irreducible representations. And what Professor Saw asked was actually very relevant to this question. First, you would like to construct indecomposable representation, which is not reducible, which is reducible, which is reducible. So first, you take a very natural indecomposable measure, and then try to find the maximal sub measure. Then take the quotient. Then that will be irreducible. Then that's first question, how to construct irreducible measure. Second question is, do they exhaust all the possible irreducible representations? That's a classification problem. Okay, that's the first problem.
This is you have indecomposable, reducible.
Yes.
And then you take a submodule and quotient.
Right. Take the maximum. Right. Right. That's the typical procedure in real algebras. So let me explain later, but anyway. And second one is what? So given an irreducible representation, how can you understand? How much can you understand the structure of representation? The first clue would be how to find an explicit basis. Or can we compute the dimension of irreducible representations? So second one is to construct explicit basis for irreducible representations. Okay. Thirdly, this is in good case, so-called semi-simple case. That means when all modules are completely reducible, then in this case, so given an L module B, we would like to find an irreducible decomposition. Okay? To find an irreducible decomposition. Okay. So, for example, if you take two tensor product of two irreducible representations, okay, and then how does it decompose? So this is usually called little Richardson coefficient. So given two irreducible representations, take the tensor product. Now if it is completely reducible, then you should be able to decompose into irreducibles. And how many times does each irreducible component occur? It is called little Richardson coefficient. So this is a typical example. And finally, well, for finite dimensional sample algebras over complex field, then every finite dimensional representation is completely reducible. So that's semi-simple case. But it usually happens when characteristic of a field is prime. And then even finite dimensional representation may not be completely reducible. Okay? So these are called the modular case. Still, given a representation, we would like to find the composition series. Okay? So composition series means that the sequence of submodules and whose quotient are, or all of quotients are simple or irreducible. Okay? Okay. So for example, given an indecomposable module, and take any irreducible representation and compute multiplicity. How many times W occurs as a composition factor of V in a composition series of V. This is called inner multiplicity. It is called outer multiplicity. So these four are fundamental problems in representation theory.
W is an irreducible.
This is irreducible. And this usually indecomposable. So indecomposable modules can have many submodules, maximal submodules, and if you take the composition series, then you would like to compute how many times does an irreducible representation occur. It is called decomposition number. So it is very fundamental. It is a very important problem in modular representation theory. For example, the Lie algebras over prime characteristic. Right, but we will focus on general linear Lie algebra, and the point is that it has direct sum decomposition of lower triangular matrices, diagonal matrices, and upper triangular matrices, which is called the triangular decomposition. Okay? Before getting into more detail, I need to explain to you what a universal enveloping algebra is. 진짜 고민되네. 이거 다 언제 하지? So there is Korean saying that you need to take time when you are in a hurry. So let's take time. Like take a pause. Right. Suppose L is a Lie algebra. And U is an associative algebra. And consider linear map I from L to U. This is a linear map.
Is an algebra just an algebra over C, or?
It is for any field, but today, in my lectures, I will focus on C. But this is for any field. I mean, this definition works for any field. So linear map satisfies the following properties. Actually, which preserve the bracket. Linear map, which preserve the bracket in the following sense. So if we take bracket, then bracket in associative algebra is the commutator. So if it satisfies following condition. Suppose we have a linear map, then the pair U and I is called the universal enveloping algebra of L if it is universal with respect to this property. So if for any associative algebra A together with the linear map say J from L to A satisfying the same condition, so jxy is the same as jx jy minus jy jx. Then there is uniquely determined algebra homomorphism, say psi from U to A, then makes the following diagram commutative. So such that psi I is J. So here L, we have linear map I, which preserve the bracket. Then suppose we have another linear map J from L to an associative algebra A, which preserve the bracket here. And then the requirement is that there is uniquely defined algebra homomorphism as an associative algebra, psi, which makes this diagram commutative. Okay. So one can say this is an enveloping algebra and U is an universal enveloping algebra. So a universal enveloping algebra means an enveloping algebra which is universal. And if you look at any textbook written by Professor Enzang Lee, then he will say uniqueness of any universal object can be proved in a routine way, or even any machine can do it. Ooh. I forgot once more that what I'm saying is being taped.
Why the word enveloping?
Enveloping. This is a Lie algebra. This is an associative algebra. And associative algebra becomes a Lie algebra. So this embraces Lie algebra. A big associative algebra embraces this Lie algebra. Yes?
Is I necessarily
linear?
injective?
It's a consequence of...
That's what I was going to say, actually. Yes, it is necessarily injective, but not trivial. Okay? So, how about the existence? So, consider tensor algebra of L. So, this is the direct sum of tensor, pure tensors. Okay, so consider the tensor algebra. So this is a free associative algebra generated by L as a vector space. And let I be the two-sided ideal of this tensor algebra generated by the following element, which is x tensor y minus y tensor x minus x bracket y for all in L for the generators of the tensor algebra. So these two are degree 2 elements. This is a degree 1 element, okay, in tensor algebra. And consider the quotient of the tensor algebra by the ideal I. Then, so we have an injection for embedding inside tensor algebra, L inside tensor algebra, and there is a quotient map, a natural projection of tensor algebra by I. Then consider the composition, which is denoted by I. Okay. Then since we factor by this idea, I would preserve the bracket, because this is the bracket inside the tensor algebra. Okay. Then by using the universal property of tensor algebra, that is an algebra homomorphism from UL to any enveloping algebra. So one can prove that U over L is the universal enveloping algebra. So existence of universal enveloping algebra is proved this way. And as your question, then is I necessarily injective? It's not clear. This is injective, but this is surjective, and the composition is not necessarily injective. And the answer is yes, and that's part of famous Poincare-Berkov-Witt theorem. So I must be injective. It takes 3 people to prove it. More than that, it takes several years to prove it. So, I mean, I would emphasize that they are not collaborators of one paper. So. And second is, if...
I don't know whether they could meet each other.
What?
I wonder whether they could meet each other, Poincare and Berkov.
I think he and he never met each other. At least I don't know.
Berkov is quite old, but...
Poincare is quite old too.
He's a person in the history. Right? Berkov is modern. Victory.
For Freely algebras, he is in the history too. But who is in history means he is already dead, right?
Long dead.
That's right. You are good. Thank you. Right, that's right. Teachers deliberate mistake, but my case is a natural mistake. I'm sorry. All right. Suppose B naught is an ordered basis. Say omega. Ordered basis of L. Okay. Then consider ordered monomials of B naught. So the set of xi1, xik, here I1, ik. So these I1 to ik are elements of the index set omega, and k is non-negative, so it contains 1 as an element. Then this is a basis as a vector space of universal enveloping algebra of L. Okay. So universal enveloping algebra is a non-commutative algebra, but as a vector space, it is isomorphic to symmetric algebra, or symmetric algebra, right? Well, polynomial algebra over L. If we have a trivial bracket, then it's polynomial algebra. Okay, that's what Poincare-Berkov-Witt theorem means. So what it says is L can be understood as a subspace or subalgebra of universal enveloping algebra. L can be embedded into universal enveloping algebra. So now here is typical exercises. I remember in one of the algebra camps of Seoul National University, on algebraic geometry, Young-Hoon Kim gave an exercise, and one of the students immediately asked, have you solved it too? Anyway, exercise is that define the notion of representations of associative algebras. Okay? Answer is what? An algebra homomorphism from, say, A to endomorphism algebra as an associative algebra. Second, define the notion of A modules, module for associative algebra. And third, prove 1 and 2 are equivalent. That's exercise. You can only imitate the argument that I gave for Lie algebras. Another exercise is that if you have L and it's right.
So very loose definition. No?
Right. So here, what is this? The universal enveloping algebra over Lie algebra can be understood as the biggest or smallest the associative algebra satisfying the defined relations of L. Okay? That's the only condition for this. That's why it is called the universal enveloping algebra. It is an associative algebra which is big enough. Still, it satisfies all the relations inside L in terms of associative algebra. Okay? For example, tensor algebra is bigger, but that does not satisfy the relations on L. Trivial polynomial algebra is smaller, but this is too small and does not satisfy the relation of L. Okay? So universal enveloping algebra is what? Largest associative algebra that satisfies the general defined relations of L. Okay? That's the idea for universal enveloping algebra. It's like a group algebra for group. Okay? So if you have representation of L, then you will have GLV and you will have a representation, right? Then there is algebra homomorphism. Okay? So if you have an L module, then you will have an UL module. Conversely, if you have an UL module, then you will have an L module because I is injective. Okay? So by Barker-Witt theorem, an L module is the same as a UL module. So representation theory of a Lie algebra is the same as representation theory of universal enveloping algebras. Same is true for groups. Representations of groups are the same as representations of group algebras. Okay? In this way, we can study the representation theory of Lie algebras using associative algebra theory. Okay. And I think I should stop here today, and I will continue tomorrow. And yes, it's better to stop here today, right? I feel it is almost a sin to give more 90 minutes lecture after 4 o'clock. So any question?